So hi, I'm Kaushik, and I'm going to talk about work that's been happening with various collaborators, principally with Roy Barkan, who's a faculty at Tel Aviv University now, and with various other collaborators and former postdocs, Luwei Yang and Audrey Delcache, and also Jim McWilliams at UCLA. And so this work spans multiple years and multiple ideas, and all of it uses this idea of using computing cross-scale energy fluxes to unravel dynamical interactions between various components of the ocean, mesoscale, submesoscale, and internal wave interactions. There's been a lot of really nice talks about each of them, and including interaction problems, including Manita yesterday by Carsten Eden and Money and lots of others. I'm sorry, I've currently forgotten, but I watched them all on the YouTube channel, and they're very useful. And thankfully, that provides a lot of background for this particular talk. So just to there's another version of a cartoon that you've seen that Manita showed earlier, and also Carsten had another one. And this basically gives an idea of what classifies the various phenomena they see in the ocean as a function of time scale and spatial scale. Okay, on the y-axis time scale, x-axis spatial scale. You have climate phenomena which are at long and large scales, and you have and also three-dimensional turbulence really at small scales. So in this particular talk, I'm not going to talk too much about the climate scale phenomenon really, and also the three-dimensional turbulence and the surface gravity effects. Those two, one of them, I'm just going to parameterize. Okay, we're going to parameterize that, and because we're studying all this, the whole study is really going to be the methodology is through high resolution submesoscale resolving ocean models. And so in these cases, we typically parameterize the three-dimensional surface motions that actually turbulence at the surface and the bottom, and we simply neglect surface gravity waves. It's not that they're not important; they are important. And a colleague of mine, Delphine Hippolyte, studies them. But the problem is that it's beyond the current scope. And so really what we want to focus on is these three components really. The mesoscale eddies, submesoscale currents, which are slightly smaller and have faster timescales, and also inertial gravity waves, which span, as Mani talked about yesterday, these are always, the frequencies of these waves are always lie between the local rotation period of the Earth, the Coriolis frequency, and the stratification frequency or the Weisler frequency. And so our interest really is in these components of the ocean, which are very strongly interacting. Now, the near-inertial waves, as Mani explained, are generated, the internal waves are generated both by storms, and these are called near-inertial waves, and also often referred to as tidally forced internal tides or inertial gravity waves or internal waves. And so our primary interest here is in the interaction between these two components. And so just as lots of people have talked about this, just a quick summary of mesoscale eddies in the ocean is that they form a baroclinic instability of wind-driven currents. They have very small Rossby numbers, and they broadly follow quasi-geostrophic dynamics. And their vertical extent extends all the way into the thermocline, okay, and which is a few hundred meters typically. So submesoscales, on the other hand, there's a snapshot of vorticity during the winter season from our submesoscale resolving ROM simulation at and this particular solution does not have near-inertial waves or tidal forcing. So we simply remove storms and tidal forcing, and so this is predominantly dominated by submesoscales and mesoscales, and it's in the winter. And so you see all these small scale eddies that you see around. These are mixed layer eddies. You see lots of anisotropic, long-lived, all these structural features. They're called fronts and filaments, and these are strongest in the surface mixed layer, very close to the surface. And they're stronger when you have deeper mixed layers. So the deeper the mixed layer, you have stronger submesoscales, and because the surface cooling during the winter season causes deep mixed layers, during the winter season is when you have stronger submesoscales. So oftentimes I'm going to be focused on things happening during the winter season. Okay, and this particular simulation I should mention is in the North Atlantic, just south of Iceland. And the length scales of these submesoscales are typically between 100 meters to about 10 kilometers. And we are on the lower end of we haven't quite resolved all the submesoscales, as it's clear. And the time scales are pretty fast, typically less than a week, sometimes as fast as near-inertial waves, as fast as F itself. And so the other thing that lots of people have pointed out, these have order Rossby numbers, and sometimes they can actually have the fronts typically have Rossby numbers even higher than 1, up to 10, 20 in the real ocean especially. And the other signal here is the surface divergence, which is closely related to the vertical velocity. And you can see that unlike the vortices, which show both the submesoscale eddies and these larger mesoscale eddies in this ocean, the divergence really picks out the fronts themselves. All these elongated anisotropic features are reflected in the divergence. So divergence is a very strong indicator of fronts. Okay, and so we'll use this later for more analysis. And to give a broad overview perspective of what's happening, this cartoon, for example, it's a depth versus spatial scale plot. Okay, on the x-axis is spatial scale and the y-axis is depth. And I've drawn out the ocean surface, the surface mix layer, the second line, and the third line is the thermocline. Mesoscale eddies extend to the thermocline, and they are generated by baroclinic instability and an inverse cascade. Mixed layer eddies are also generated by a special kind of baroclinic instability called the mixed layer instability, which is relevant for the well-mixed surface layer. And these have a inverse cascade to large scales. Okay, great. Thank you very much. So the fronts themselves are also formed of a surface mixed layer, but there are even smaller scales in mixed layer eddies. Okay, so as long as early as 2008, the Capri et al. Paper tried to estimate that maybe frontogenesis has something to do with the forward energy flux that is seen at fronts. Okay, and the Schubert paper really laid down the idea of how mixed layer instability coupled with inverse cascade to mesoscales is a prominent feature of mixed layer eddies. So really, this particular, I'm going to start off by talking about the interactions, but understanding how is the forward energy flux at submesoscales and what's the connection of that to frontogenesis. That's my subject of this paper in JPL last year. And so, did my screen just suddenly turn blue? Sorry. Sorry, I apologize. I'm not sure what happened here. I have no idea why. Okay, so the methodology we're going to use is what's called the cross-scale energy flux. In this case, you take all your flow variables here. I've written U, but it's actually every flow variable, and use a smoothing filter. Typically, it's like a low-pass filter. What it does is that it creates separates given a certain scale, it separates out your flow domain into large scales and small scales. Okay, so U prime is a small scale, U tilde is your large scale, and U tilde is basically a smooth version of U. Okay, you can do this in different approaches. You can use a horizontal spatial filter, you can use a temporal filter, or you can use a vertical filter. In each case, you will get a different idea of what small scales or large scales means, or you have a slow scale and a fast scale decomposition, and a higher scale versus a high versus low mode decomposition. Here, I'm really going to talk about the horizontal smoothing scale, because we want to talk about horizontal fluxes. Okay, so if you do that, you can actually write equations. So corresponding to U tilde, there's a capital E, that's the large scale energy, and corresponding to U prime, there's a small scale energy E. You can write equations for these. These are just a structure of the equations. So the point here is that, so there are two important terms here. One is the transport flux. That's the first one here. It tells you how these energies are transported around the ocean. And the second is the exchange term, which is the cross-scale flux, which tells you it is the exchange of energy between the small scale energy and the large scale energy. Okay, this is always going to be true for any exchange term. It's going to talk about it's going to be equal and opposite. It's like a sort of a Newton's law, but that's what it's here. This is the exchange term, and this is the one we're going to focus on to understand how the energy, by diagnosing this quantity, which reflects for different scales, how the energy flows across the ocean, we can understand the dynamics of interaction between various components. So that's the primary objective. So the nice thing about them is that unlike spectra or probability distribution functions, these fluxes give you a direct insight into the dynamics. The negative, of course, is that they are much more expensive to compute. Okay. And so I'm going to write down how they look like. So the structure of these things looks like it's a sum over U, V, and W. Looks like a small scale. Remember, the U prime is the small scale and the U tilde is a large scale. And it looks like a large scale strain, which you see the DDX term, and a small scale Reynolds. It's a Leonard stress actually, but I've written it as a Reynolds stress. But it's an eddy momentum flux of the small scales. Okay. Typically, the idea would be that for a given scale, if your pi is larger than 0, then you have a forward energy flux, which means energy going from large to small scales. And if it's negative, it means it's an inverse energy flux, energy going from small scales to large scales. Typically, you can actually break this pi into horizontal and vertical terms. So for example, the horizontal terms have all the horizontal strains, and the vertical term has all the vertical shears. I haven't written down explicitly for simplicity, but this is a broad thing. When you don't have internal waves, like for example, the simulation I just showed you previously, when you have no internal waves, basically no forcing of no tidal forcing or no storm forcing, in that case, the vertical term is actually quite small. There's good reasons for this. So in the first part of the talk, when the horizontal terms are really when there's no waves, the horizontal part of the energy flux is the one that dominates. Okay, but this idea that it's a product of a small scale stress and a large scale strain is a very useful way to think about it. Okay, that's what the flux is. The question is, how do you visualize it? So what we've done is that we've picked a whole bunch of filter scales. These L's are the filter scales for different smoothing scales. We get a different pi, and this pi is a complicated function of the space x, y, z and time, right? So there are two ways you can visualize. You can just directly visualize pi. For you can fix L. You can take a certain smoothing scale and just visualize how pi looks like in space and try to understand what it means. Okay. The other simpler and a better starting point is simply average the pi over some things. For example, in this case, I average over horizontal space in a certain region of. This is in a certain region of North Atlantic that the simulation I showed you, and over a season, because we're looking at submesoscales, we're interested in submesoscales, which I told you was strongest in winter. I'm going to average this over the winter season of the North Atlantic. Okay, and so basically now we want to look at the average flux in this region, averaged over space and over season. Okay, and this is a plot, and this it shows you the cross-scale energy flux is a function of depth. The vertical axis is depth, and the horizontal axis is the inverse wave length scale. So normally it's like a wave number, really. So basically on the right-hand side are the small scales, and on the left-hand side are large scales, just like a wave number. So what you see here, and here I don't have the color bar here, but in all the in the entire talk, whenever you see a blue color, it means it's less than 0, which means inverse flux. Whenever you see a red color, it means it's greater than 0, so it's a forward flux. So what you see is that at small scales you have a forward flux, and at large scales you have inverse flux. What's interesting is that the 500-meter resolution model resolves the forward flux, but the 2-kilometer does not resolve this forward flux. Okay, and what's even further, the inverse cascade in 2 kilometers is also weaker. So you have two things. When you go from 2 kilometers to 500 meters, both the inverse cascade has gotten stronger, and the actual forward flux is starting to be seen. Okay, and so we can do a little more analysis to understand how to kind of unravel the different components of it. And the one thing we do is what's called a Helmholtz decomposition. The Helmholtz decomposition is a general framework of mathematical framework of expanding any field, vector field, into rotational and divergent components. So here that's a decomposition, and so the idea here is that if you do this decomposition, I mean once you do it, then all the vorticity, which is the zeta here, all the vorticity is explained by the rotational velocity field, and all the divergence is explained by the divergent velocity field. So it's almost orthogonal separation in some sense. Okay, and so now what we do is we compute these energy fluxes purely using the rotational velocities. Remember, we had this. This was an energy flux equation, and what we do is that first we take all the u's here to be purely rotational. And when we do that, we have two terms. One is the rotational flux, and the remainder, the total flux minus the rotational. If you do that, you find that you have a very clean dynamical separation between the rotational and between the forward and inverse flux. Almost all the energy flux on average is in the rotational components, which means all the rotational components are exclusively responsible for the inverse energy cascade, but the forward energy flux is explained by the remaining. It's a mix of divergent and rotational components. Okay, so the dominant hypothesis, as I write below, is that mixed layer and mesoscale eddies are actually losing energy to the fronts. The question is, I mean, I haven't explained this to you, but this is the mechanism that's actually happening. So just to clear this up, we have separated the inverse and forward energy flux into different components depending on whether it's rotational or not. And what really when you actually add these two, you see that there's an overlap region where you have mixed layer eddies which transfer energy to large scales and also to small scales through frontogenesis at fronts. So this is a dual energy cascade. Okay. And so the next part you can actually do is, remember I said that you can either visualize it or you can look at averages. So let's do a simple visualization. And so here, for example, I'm showing you the same thing. There's 4 plots here. Forget about the first top left for the moment. The second is the vorticity I already showed you, the divergence I already showed you before, and the buoyancy gradient also tracks the fronts. It's the surface buoyancy gradient is a strong frontal signature. And the first one is actually the energy flux at 4 kilometer scales. Remember how I said that at 4 kilometers, typically that's where the fronts, that's a submesoscale regime. So if you look at that 4 kilometer visualization, it's a single snapshot. You notice that it very closely tracks the divergence. It does not track the buoyancy gradient because you can see strong buoyancy gradient fronts, which do not show up here particularly strongly. So what this means is that at 4 kilometer scales, the horizontal energy flux really is at fronts. Okay, and the average energy direction, it's not quite obvious from this, it's forward. So if you average the signal, the signal I showed you here, the pi at 4 kilometers on fronts, then you find that it's actually proportional to the convergence. It's a very strong relation. It's almost linear across the season. Okay, so this relationship is the question is, does it have a theoretical origin? And the answer is yes. First, I want to talk about briefly talk about a theoretical idea by my colleague Roy Barkan, where he showed that frontogenesis theory in the ocean. Frontogenesis in the ocean is primarily driven by divergence. So the horizontal so the three quantities, the equations of change of divergence, vorticity, and buoyancy gradient are all governed by the divergence. And this is the kind of dynamics you see. This is a theory of frontogenesis that Roy proposed. And in this paper, we actually further show it's consistent with this relationship that you have here. We show that even the energy flux at small scales is also driven by is also controlled by divergence. So what this means is that putting all these things together, you can actually you would say that the forward energy flux that you see at small scales in the ocean is potentially due to frontogenesis. Okay, I haven't put this out, but there's recent evidence by Alberto Navarra Garbato and his collaborators, where they show in the osmosis array that this is a very strong result. So this theoretical idea, which appears in the ocean models, is also seen in the observations. So next, I want to actually talk about, till now I've talked about solutions which have no eddy, no waves of any sort, no internal waves, no initial waves. The question is, what happens if you actually have internal waves? In this case, what we do is that we actually do an eddy wave decomposition. We decompose the flow, the small scales and the large scales, into large and small eddies, small scale waves and small scale eddies, and large scale waves and large scale eddies. So if you plug this in this equation, what happens is that you have 8 different terms, because each of these u's has 2 possibilities. So you have 2 to the power of 3, that's 8 different terms, and these look like triads. So basically, you have large scale eddies interacting with small scale eddies, and so on and so forth. So all these have well-defined in the ocean. They have well-defined dynamical implications. But thing is, some of these terms are really weak in the ocean. We find them almost everywhere we look at it, and for good dynamical reasons, they're all pretty weak. And so the one I'm going to remove and not worry about is these 4 terms, which are really small, and only focus on the rest of the terms. And let's see what they actually mean. So I've written out the 4 of these important triads. The first one is the pure eddy interaction between eddy components. And this eddy here involves both submesoscales and mesoscales. Okay. And the second is the wave interaction terms. One of them is the wave, where involves a rectification of waves into the mean flow, the wave mean flow interaction, and the second is a wave interaction. Okay, the third term is the wave scattering term. Zoe earlier talked about gave a talk about it, and so her results would be basically captured by this particular term. So where a large scale wave, remember the capital W means large scale wave, the large scale wave loses energy to small scale wave and eddy interactions, small scale waves catalyzed by small scale eddies. Okay, so this quantity is the wave scattering term. So the question is, how do we do the eddy wave decomposition? There's lots of ways. You can use time filtering. You can use other ways. Here, I mean, Manita talked about a slightly more sophisticated approach. So I haven't really looked into that because it's not clear how easy it is in the models. But here we use a method by Wang et al., where it's a relatively simple idea which looks at the relative strength of the rotation and divergence to classify waves. Okay. And so, for example, here's an illustration in the Luzon, is in the Western Pacific, in the Luzon Strait. You have, so on the leftmost, you see that I'm showing you the zonal currents, which are the eddy flow. You see the Kuroshio. If you look at the top left curve, you see the Kuroshio and all the various currents. And the bottom left, you see these small scale waves being radiated away from the Luzon Strait. So just to be clear, China is in the top left corner of each figure, and this is Taiwan and Philippines. So the Luzon Strait is the strait in the middle, and it has a very strong tidal signature. Okay, so, and you can see that the vorticity of the eddy field is like very vertical, and the divergence of the waves, you can see these wave fronts propagating eastward, sorry. And so anyway, once we do the eddy wave decomposition, and we can just like we computed the total energy fluxes, we can compute all these different terms. And in 2 recent papers, we actually studied we diagnosed these terms and looked at what are the implications for eddy wave interactions. Okay, and so the first one was led by Roy Barkan, and in the North Atlantic, which has very strong winter near-inertial waves and submesoscales, and the other by Audrey Delpeche, a former postdoc in the California current system. In both places, they found, unfortunately, I don't have time to discuss these in detail. Both places they found, but the wave interactions are really weak, and the dominant interactions are the wave scattering by eddies and the eddy interactions. Okay, this is kind of surprising because you think that wave interactions are very important in the ocean, but in 2 major regions, these actually are very weak. And so in a concurrent study, our postdoc Luei Yang, and it's the reference at the bottom right, she did a really nice study where she compared, again, she looked at the eddy wave ROM solution with a wave only ROM solution, which means you remove the eddies and you only have a pure wave forced ocean. And in these cases, she found that the initial internal wave, this just shows the frequency spectrum of the flow, and the black and the red, it's not important what the differences are. The black is the is the eddy wave spectrum. And it has you can see it has an internal wave continuum where the wave only has a pure it's only all you see is harmonics. You don't see the internal wave continuum because the internal wave continuum is a fundamental property of the ocean. You see it everywhere. So the fact that the wave only simulation cannot reproduce it everywhere, whereas the eddy wave is, coupled with the idea that the wave-wave interactions are very weak and the scattering terms are very strong, basically let's just conclude that you can form an internal wave continuum without wave-wave interactions. So this is consistent with theoretical work by Kafiabad and Cox and others, but they had a very idealized setting, and this is in a realistic ocean model, submesoscale resolving ocean model. Okay. Yeah, I'm almost done.
One more minute.
I'm just going to finish. Okay. So the final thing I want to show is that the same residue. I said that in many parts of the ocean, like the California Current and the Iceland Basin, the wave-wave interactions are very weak. But in the Luzon Strait, which has the strongest tides in the world, these are important. Just to kind of reprise, we have this shows the eddy interactions from this method, from this wave decomposition. And here you see in the bottom is the winter season, the top is the summer season. You see the forward flux, you see the inverse flux. And you see that in the top, the summer season, the forward flux disappears because there are no submesoscales, as we talked about before. But the most interesting part is that the first one here is the pure wave-wave interaction. The second one is the wave scattering terms. And you see that now both are comparable order. So now in this particular region, unlike the region, the California Current and the North Atlantic, you do actually have strong wave-wave interactions, and these are important. But what's interesting is that they actually are pretty weak in the winter, which is strange because the tides are as strong in the winter as they are in the summer. So what happens in this region is that in the summer, you also have really strong storms. So basically, the storms generate near-inertial waves. The Luzon Strait generates tidal internal waves, and these two interact with some pretty strong internal wave-wave interactions, and that's what's actually happening here. So, in any case, the basic idea of it is that this approach is a pretty effective, honestly, because you can see how clean the decomposition is between different terms. This methodology of using cross-scale fluxes is a very efficient approach to study the interaction between different components in the ocean, and I think and relates to many different talks that actually have happened in the past 2 days. So anyway, thank you so much.
Thank you. Any questions from here?
Am I audible?
Yeah, I can hear you.
Yeah, I had a couple of questions actually.
Okay.
So when you were talking about using divergence to track your submesoscale fronts, so I was wondering about that. I get what you're saying about this more recent theory of frontogenesis that your colleague has presented. If you go back to like
yeah.
If you go back to like the really old theories, like you go back to like Hoskins in 1975, 82.
Yeah. Yes.
Really thinking in terms of confluent, non-divergent geostrophic flow driving the initial part of the frontogenesis.
Correct.
And this small ageostrophic assist that's causing this further convergence. But now you're using. So I've mostly seen people use horizontal gradients and buoyancy to track to define fronts. But you're using divergence as your definition of a front. Is that correct on this slide?
Yeah, because actually horizontal buoyancy gradients are not the right metric to look at fronts. They're placed in the ocean where you have pretty horizontal, very strong horizontal buoyancy gradients. But I see what you're saying. Yeah, but typically I would think of divergence as the primary what defines frontogenesis, not buoyancy gradients.
So in effect, you're redefining fronts in a sense to capture what you consider the dynamically unique effect of fronts, which is that they have a strong vertical circulation.
Yes, exactly. Yes, that's right. And I think just to comment on Hoskins and Bretherton, the thing is even because typically the Hoskins and Bretherton mechanism in the ocean is referred to as strain-induced frontogenesis. Right, so we say they have mesoscale strain, which creates the conditions for frontogenesis to happen. But in the ocean, actually, it's a pretty weak mechanism. So in the ocean, the dominant mechanism is in fact mixed layer eddies and vertical. It's something called turbulent thermal wind, which connects the interaction between geostrophic balance and surface turbulence. And this is a much more pervasive mechanism. In fact, if you look at this particular, sorry, I have this one figure. This one, right? You can see that the forward flux is primarily at small scales. So there's no non-local large-scale flux happening directly from large-scale straining of mesoscales to small scales. So in the ocean, the Hoskins and Bretherton mechanism is really not that important, in my opinion. And I think we have upcoming work which will, I think, pretty decisively show that this is the case. That the strain-induced frontogenesis in the ocean, while important in certain cases, in terms of energetics, is not that important. It's relatively rare. So.
Okay. One other thing.
Yeah.
So, I mean, this is not really worth much. It's a pinch of salt, but your work and a lot of the literature seems to suggest that you have these fronts that are intensified at the surface, and that die off as you approach the thermocline, as you approach the base of the mixed layer. But
I think this figure is basically a representation of that, really. I mean, in terms of energy fluxes,
Yeah, but so I don't know about this in terms of energy flux, but there was this COCO model, so basically another regional ocean simulation, not ROMS, but another.
Well, actually, CROCO has a ROM score. It's derived from ROMS.
But with topography following contours and small changes.
It's ROMS is a topography following
So there was a CROCO model run of the Mozambique Channel by Pierrick Penvin that Florian Sud was analyzing, that I've worked with, and there they were looking at thermal fronts. So they were just looking at horizontal gradients in temperature, and they found that those are actually maximized at the mixed layer base, so at the upper thermocline and not in the near the surface. I just wanted to know if you had any comments on what could be.
Yeah, so the thing is that, right, so if you're looking at pure temperature is tricky because there's compensation between temperature and salinity. Right, the ocean has very strong compensation between temperature. So you can have fronts which are frontal in temperature and salinity, but have very weak signature in buoyancy.
Right.
Does that make sense? So basically those, I think, sorry?
Density compensated fronts, basically.
Exactly. So they're compensated fronts. I mean, I don't think these kind of ideas don't necessarily apply to those. So I don't think they would have a strong dynamical presence in the, for example, convergence. So the idea is that your scalar flux, I mean, your buoyancy flux or your temperature salinity flux must really feed back on the momentum fields in some way. And so in this case, that actually happens, right? The surface divergence, in some sense, is directly connected to the buoyancy gradients. But it's possible to have I mean, in observations that I've seen recently using shipboard measurements, you see really fine thermal fronts, really crazy actually, but they have very low buoyancy associated buoyancy signature because of this compensation. Caitlin Wayland, for example, in her talk, she talked about some of these issues about the level of compensation using the Turner angle. So you can have scenarios where you have the Turner angle is in such a way that you have very strong one or the other.
The Turner angle was low in her map in the channel of interest, but yeah, I get your point.
Yeah. So I mean, but yes.
Thank you. There is one last question from somebody on Zoom. Would you like to unmute yourself and ask it?
Yeah. Can you hear me?
Yes, we can hear you.
Yeah. So the first question is related to the ROMS that you use. If I'm not wrong, it uses a hydrostatic balance in the vertical.
Yes.
And when you're simulating Rossby order 1 simulations, do you think that's valid? That still stays valid?
Yes, absolutely. So there's a difference between hydrostatic balance and Rossby number, which relates to horizontal advection. That's from the horizontal advective terms, right? So the breaking of hydrostatic balance is, you would think of it as non-hydrostatic phenomenon, and that's when you have order 1 aspect ratio of a phenomenon, typically three-dimensional turbulence. This includes instability, like symmetric instability, and boundary layer turbulence, and so on and so forth, or convection, right? But fronts, even fronts are still not even close to, even in the real ocean, are nowhere close to order 1 in their vertical aspect ratio. So, I mean, I've seen some really strong fronts in observations. I mean, I've actually tracked some of these things, and you see like 10 to 100 meter front, 100 meter fronts, but even there, the mixed layer is still pretty shallow, right? And so you don't really. So, for example, we've run non-hydrostatic simulations where ROMS has a non-hydrostatic version where you don't assume hydrostatic balance, right? And you can run these together at the same resolution, and they find no difference at all.
I see.
Because that's the point. Yeah.
So the other question is. Oh, sorry.
Sorry, we are very late with time. Yeah, unfortunately, we have to stop. Thank you very much, Kaushik, again for your very nice talk.
Thank you so much for having me.
Thank you.